Welcome to Lecture 6.2, Field Automorphisms. Recall that an automorphism of a group G was an isomorphism from that group to itself. We will define automorphisms of fields similarly. Here's the formal definition. Let F be a field. A field automorphism of F, or just automorphism of F if it's understood that it's a field, is a bijection phi from F to F such that for all elements A and B in F, or just numbers in F as we often say, phi of A plus B equals phi of A plus phi of B, and phi of A times B equals phi of A times phi of B. In other words, phi must preserve the structure of the field. Compare this to an automorphism of group, which is a structure-preserving map from the group to itself. Now, if our group was written additively, then phi had to be a homomorphism, so it satisfied this condition, phi of A plus B equals phi of A plus phi of B. However, if phi was written multiplicatively, then it satisfied this condition, phi of AB equals phi of A times phi of B. Now a field is both an abelian group under addition and an abelian group under multiplication if we take out 0. So it must satisfy both, or phi must satisfy both of these properties. It preserves the structure of addition and preserves the structure of multiplication. For example, let F be the field Q adjoin root 2. On your homework, you will verify that the following function, phi from this field to itself, defined as follows. It sends A plus B root 2 to A minus B root 2, that is an automorphism. In other words, you have to show explicitly that phi of the sum of two elements, let's say A plus B root 2 plus C plus D root 2, is equal to, so I'm putting ... here, phi of A plus B root 2 plus phi of C plus D root 2. It's not hard. You just need to basically plug in the definition and then rearrange terms and show that this holds. Well, that shows this first part. Next, you need to show that it is a multiplicative homomorphism. In other words, that phi of A plus B root 2 times C plus D root 2, so multiply these things out, apply this function. In other words, swap the sign, S-I-G-N, of everything in front of a root 2, and show that that is equal to phi of A plus B root 2 times phi of C plus D root 2. And you also need to show it's a bijection, but I claim that that's clear. That it's very clear that this function is not only onto everything on the right-hand side gets hit, but also that it's one-to-one. Here's a question I'd like to pose. What other field automorphisms of Q adjoin root 2 are there? Well, there's clearly the identity automorphism, the map that just fixes everything. But can you think of something else? Open-ended question. We will answer that later. Field automorphisms are central to Galois theory. In fact, the Galois group of an extension or of a polynomial is a group of automorphisms of a certain field. We'll see more details shortly. But first, here is a defining property of field automorphisms. If phi is an automorphism of an extension field F of Q, then this says that phi fixes every rational number. So phi of Q equals Q for all rational numbers Q. Let's prove this. So the automorphism phi is a bijection, so it sends 1 to some rational number Q. Let's try to figure out what Q can be. Clearly, Q cannot be equal to 0. Think about why this is. Well, if it were, then phi of 2 would be phi of 1 plus 1, which is phi of 1 plus phi of 1, which is 0. And all of a sudden we don't have a bijection because 1 and 2 both get sent to 0. So Q is not equal to 0. Observe that Q, which is defined to be phi of 1, is phi of 1 times 1, clearly. And then by the property of a multiplicative homomorphism is equal to phi of 1 times phi of 1, which is equal to Q squared. So what rational numbers Q are equal to their square? Well, there's 1, minus 1, and 0. And we've already eliminated 0. Similarly, Q is equal to phi of 1 by definition, but that's also equal to phi of 1 times 1 times 1, which is phi of 1 times phi of 1 times phi of 1, which is Q cubed, and so on. So now what? We have a rational number Q that is equal to its square, that is equal to Q squared, and equal to Q cubed. So the only rational number that does that is 0 or 1, and we've eliminated 0, so Q has to be 1. Now if you want to, you can say that Q to the n equals Q for every Q greater than or equal to 1, so Q has to be equal to 1. And that's the end of the proof. I forgot my box, but I'll just put it right there. Here's a simple corollary of this proposition. Root 2 is irrational. Let me say a few words about why. Well, on the previous slide, we constructed a field automorphism from Q of root 2 to Q of root 2. I think we called it phi. Yeah, phi. And it was defined by sending a plus b root 2 to a minus b root 2. And then I asked you to verify in the homework that this, in fact, was an automorphism. But notice that phi of root 2 equals negative root 2. So if we proved that any automorphism of an extension field of Q fixes everything in Q, and here is an automorphism of an extension field that does not fix this particular number, root 2, then this number cannot be in Q. So this is an alternative proof that root 2 is irrational. It uses a lot more high-powered theory than probably what you were used to when you saw your first Intro to Proofs class. Remember how that proof went? So assume root 2 was rational. So you assume that root 2 was equal to a over b. And then you squared it and you got that 2 equals a squared over b squared, and then you arrived at a contradiction from there. So really simple proof. I like it. I think it's cute. It's a proof using Galois theory. Speaking of Galois theory, well, that's a term that I've thrown around a lot, but I have yet to define exactly what it is, so I think it's time to do that now. So the set of all automorphisms of a field form a group under composition. Here's the formal definition. Let's let F be an extension field of Q. The Galois group of F is the group of automorphisms of F, and we denote this as Gal of F, or just the Galois group of F. So for groups, we called it the automorphism group of G, and here I guess we could define the automorphism group of F, but we are going to call this the Galois group of F and define that to be the automorphism group. Here are some examples without proof. First of all, the Galois group of Q adjoined root 2 is, well, technically isomorphic to C2. So I asked you to think about what other automorphisms of Q adjoined root 2 were there besides the identity and the one that sends a plus bi to a minus bi, which, if you want to abbreviate, you can write it like this because we know it fixes the rational number, so it fixes the a part. So you can define F as the automorphism, or the mapping that sends root 2 to negative root 2. And in fact, these are the only two automorphisms of this field. A little bit of a trick question. So the Galois group has two automorphisms, so it has to be isomorphic to the only group of order 2, namely C2. Next, an automorphism of Q adjoined root 2 and I is completely determined by where it sends root 2 and I, respectively. There are four possibilities. There's, of course, the identity map E, let's call it. But also, there's the map that swaps the sign of root 2. So h of root 2 equals negative root 2, and h of I equals I. There's the map that fixes root 2 and swaps the sign of I. So v of root 2 equals root 2, and v of I equals negative I. And there's the map that swaps both of them. So v of, let's call it r of root 2 equals negative root 2, and r of I equals negative I. Now I've defined these mappings using the letters h, v, and r to suggest, to hint at, that the automorphism group, or the Galois group of this field extension, is isomorphic to the Klein 4 group V4. Because remember, when we first saw V4, we saw it as containing four elements: a horizontal flip, a vertical flip, and a rotation, which is what you get when you do both of these flips independently. In other words, the Galois group of this field extension is generated by H and V, these two automorphisms, or really any two of these automorphisms will do, and it is isomorphic to V4. Let's do another example, and as I've done previously, I will introduce this with a question. What is the smallest extension field F of Q, that is the rationals, that contains all roots of this polynomial, g of x equals x cubed minus 3? So this is the first example that we've seen where we're looking at roots of a polynomial of degree more than 2. Let's begin by letting zeta denote the complex number e to the 2 pi I over 3. This is in polar coordinates, but in Cartesian coordinates this is negative 1/2. It's the real part plus the imaginary part, root 3 over 2i. So here's a picture of the complex plane over on the right. And recall that every number on the unit circle has the form e to the I theta, where theta is the angle from that number to 1, which is right here. So e to the 2 pi I over 3 is on the unit circle at angle 2 pi over 3 radians, so that's 1/3 of the way around. And theta squared, remember how you multiply complex numbers? The angles add and the lengths multiply. So you multiply this by itself, the length is still 1, and the angle just doubles, so that it gets down here. So that's e to the 4 pi I over 3. And similarly, zeta cubed, you just rotate it 3 times and you go right there, or twice I should say, to get zeta squared, and then one more time to get back to 1. Zeta is called a third root of unity, unity just meaning 1, and that just means that it is a cube root of 1. Formally, that means it is a root of the polynomial x cubed minus 1, which, by the way, factors as x minus 1 times x squared plus x plus 1. This degree 2 polynomial has two roots, which are zeta and zeta squared, and then the third root of this polynomial, of course, is 1. So all of these are third roots of unity, although we call these two primitive third roots of unity because they are not roots of any lower degree polynomial. So this is a first, let's say a primitive first root of unity. These are primitive third roots of unity. Next, I want you to notice that the roots of g of x is this polynomial up here, x cubed minus 2, are the following. Well, first there's the real cube root of 2, then there's the cube root of 2 times zeta, and then there's the cube root of 2 times zeta squared. So to see why this is, let me show you both algebraically and geometrically or graphically. Well, z2 cubed is, it's hard to draw zeta, I almost forgot, zeta cubed times cube root of 2 cubed, and obviously zeta cubed, as we said, is 1, and these cancel, so we get 2. And similarly for this one, zeta 3 cubed is zeta, that's not quite a zeta, but that's close enough, zeta squared to the third, which is zeta to the sixth, times the cube root of 2 cubed, which is also 2, because zeta to the sixth, if you go around 6 times, 1, 2, 3, 4, 5, 6. So both of these clearly solve x cubed minus 2. If you want to see graphically why this is, now the cube root of 2 is approximately 1.26, so if I were to draw it on the unit circle, it would be around, well, let's make that a little better, it would be around there, so this is the cube root of 2. And then I'm going to exaggerate a little bit just so I can fit it in. There's going to be one up there. That's zeta times the cube root of 2. And then down here, again, I'm going to exaggerate just so I don't write over this. This is going to be zeta squared times the cube root of 2. And notice that if I multiply this by itself, or if I cube this thing, then the angles add. So if I multiply this by itself, it rotates over here and it gets a little longer. So I would say it would get to be about there, because the lengths multiply. So whatever 1.26 times 1.26 is, that's the distance of this. And then when I multiply it again, I get it rotate. Let's rotate it one more time. The lengths multiply, so now I get a length of 2. So this is 2. And the angles add, so I get back to the real axis. So graphically, multiplying this by itself 3 times, or cubing it, gets here and then gets there. And similarly, if I multiply this guy by itself, or if I cube this thing, then, well, zeta squared, angles add, it gets up here a little bit longer, and then multiplying it by, I guess this has a name, I can call it z3, multiplying it by z3 again, adds this angle, and you get back to 2. So there's 2 different ways to see why these things are the roots. Clearly, the field that we seek, the smallest extension field f of q that contains all the roots, can be constructed by just starting with q and throwing in the roots and seeing what that generates. But I claim that there's a better way to write this. That I don't need to throw in all 3 roots. All I need to do is throw in zeta and throw in the cube root of 2. Let's try to understand why. Notice, first of all, that this field contains z1, z2, and z3. Because it contains z1, there's z1. It contains z2 because I can multiply zeta times cube root of 2. And it contains z3 because I can multiply zeta by itself, get zeta squared, and then multiply that by the cube root of 2 to get zeta 3. So we just showed that everything in this field is contained in that field. So that shows that we have a subset inclusion like that. We have containment like this. So this thing is at least as big as here. Let's now argue why everything in here is also in here. So all we have to do is show that if we can produce zeta and the cube root of 2 from this field, then we're done. Well, clearly, the cube root of 2 is in this field because it's just z1. So I claim that I can construct both of these from just z1 and z2 using arithmetic. And so how would I do that? Well, what if I take z2 and I'm allowed to divide by z1, then I get zeta. And so indeed, every generator of this field is in that field, and that proves this containment. So they have to be equal. And that establishes this claim, that our field F is equal to Q adjoined zeta and cube root of 2. A little bit of algebra can show that this field extension of Q, that is Q adjoined zeta and cube root of 2, can actually be written as this set of complex numbers, namely a times 1 plus b cube root of 2 plus c cube root of 4 plus d zeta plus e zeta cube root 2 plus f zeta cube root of 4, where a, b, c, d, e, and f are all rational numbers. In other words, the following set is a basis for this field extension over Q. Let me put a colon there. So 1, the cube root of 2, the cube root of 4, which is just the cube root of 2 squared, zeta times the cube root of 2, and zeta times the cube root of 4. So that's our basis. And it's not hard to see why everything can be written like this. Let's do it like we did in the previous lecture. So let's start with Q adjoined zeta, then adjoined the cube root of 2. So things in here we can write as, well, I should say this is a degree 3 extension because this is a degree 3 polynomial. So we can write things like, or this like alpha times 1 plus beta times the cube root of 2 plus gamma times the cube root of 4. That's all we need, because if we take this thing and cube it, then we get a rational number 2. Now alpha, beta, and gamma all live in this field, Q adjoined zeta, and so they can actually be written as, so alpha can be written as a plus b times zeta, and then beta can be written as c plus d zeta, c plus d times zeta, and then times the cube root of 2, and then finally gamma can be written as, what do we have, e plus f times zeta times the cube root of 4. And then if we multiply this all out, and we will get something that looks like this. Now I may have permuted my c's, d's, e's, and f's. It doesn't matter. I feel like I was going to tell you something else about this. Oh yeah, so I have a zeta here, but I don't have a zeta squared, and there's a zeta squared over here. Well, why is that? So several reasons. First of all, zeta squared can be generated by zeta. So if you take zeta and you take negative zeta, maybe it's easier to look at when you take negative of this. So negative zeta is over here. This is negative zeta, which is positive 1/2 minus the square root of 3 out of 3I over 2. And then, so if I start with zeta and I take negative zeta, and then if I subtract 1 from it, then this just, well, then I get zeta squared. So in other words, zeta generates zeta squared, so I don't need both of these. And also, because zeta and zeta squared are roots of this degree 2 polynomial, first of all, you can see right away that zeta squared, and I've set this equal to 0, you can see right away that zeta squared is equal to negative zeta minus 1, as I claimed. And so this is actually a degree 2 extension. So we only need 2 things, namely 1 and zeta. So again, to derive this, I say a little bit of algebra. Here it is. Write an element, an arbitrary element of this field adjoining cube root of 2 like this, and then each alpha, beta, and gamma actually can be written as such. A plus b zeta, c plus d zeta, and e plus f zeta. Let me conclude this slide with one more observation about this extension field. So since zeta lies in Q adjoined zeta and cube root of 2, then so does zeta plus 1/2 times 2. And notice what that is. If I take zeta and I add 1/2 to it, then this negative 1/2 goes away. And if I multiply by 2, I get root 3i, which is just the square root of negative 3. Therefore, I can write the extension field q adjoined zeta and cube root of 2 as q adjoined root negative 3 and cube root of 2, which is just q adjoined root 3i and cube root of 2. And we can do this because these two numbers, zeta and cube root of 2, clearly generate these two numbers, square root of negative 3, that's what we just verified up here, and obviously cube root of 2, it's the same thing, and vice versa. From these two numbers, if I start with root negative 3, I can then divide by 2, and I can subtract 1/2 to get zeta, and then I can generate these two numbers. So these are just two different ways to express the same field. Some people like writing it like this because, well, one advantage to that is if you look at the square root of negative 3, you can see right away that that is a root of x squared plus 3. So it's arguably clearer that q adjoin the square root of negative 3 is indeed a extension of degree 2, where it wasn't quite so clear that q adjoined zeta was an extension of degree 2, at least not until we saw this polynomial here, x squared plus x plus 1. Now, I want to turn our attention to the subfields of q adjoined zeta and cube root of 2. So this set is the full field, but what if we only take some of these elements? Like, for example, you can take q and adjoin the cube root of 2 only. That's going to be a subfield, and it's clearly not equal to the entire field because it's contained in the real numbers. We could also take q and adjoin just zeta. Or we could take q and adjoin the cube root of 4, and so forth. Or we could adjoin the product of these two things. And it's not clear that we're going to get different fields in all of these cases, and actually in some cases we don't. For example, let's compare q adjoined zeta squared to just q adjoined zeta, and actually it's not hard to see why these are the same field. One way to see it is if you take zeta squared and you square it, you get back zeta. So from zeta squared I can create zeta, or generate zeta, and from zeta I can create zeta squared. And therefore these field extensions are the same. And both of them consist of all numbers of the form a plus b zeta, where a and b are rational. And there's other ways to see this too. As I think I mentioned before, zeta squared is actually just equal to negative zeta minus 1. Here's one that's less obvious. I claim that the field you get when you adjoin the cube root of 2 and the cube root of 4 are actually the same thing. And here's how to see that. So let's take the cube root of 4, and let's see if we can use it to generate the cube root of 2. And we can do that. So if we square it, we get 2 cube root of 2, and then we divide by 2. So we have used this thing to generate cube root of 2. And similarly, if we start with the cube root of 2 and we square it, we get the cube root of 4. So either one of these things can generate the other via operations of arithmetic. Therefore, these two fields are the same set of numbers, and both of those are all real numbers of the form a plus b cube root of 2 plus c cube root of 4, where a, b, and c are rationals. It turns out that there are two more subfields, and as we did before, we can arrange them in a lattice. Recall we did this for, I think it was the field 2 adjoined root 2 and root 3. Do you remember that? So we had q adjoined root 2, q adjoined root 6, and q adjoined root 3. Those are all subfields, and they all contained the rationals. So we got this lattice, which looked just like the subgroup lattice of the Klein 4 group V4. Well, now let's do that with this field. Here is the subfield lattice. Does this look familiar? And let me mention that I've labeled these edges with the degree of the extension. So I start with the rationals. To get up to here, I have to adjoin a root of a degree 3 polynomial. And same thing with these things. So it's not completely clear that these are different fields, but I encourage you to play around with this on paper and see if you can verify that you cannot create zeta squared times cube root of 2 from just zeta cube root of 2 and vice versa. And it's also not clear that there's not other fields lurking in here besides these. But let me ask you, does this look familiar? Here is the subgroup lattice of D3. Notice it is identical in structure to the subfield lattice, well, assuming I turn this one upside down. And even the edge labels are the same. For example, this 3 is the degree of this field extension. It's because I can create this field by adjoining a root of a degree 3 polynomial, namely this root, to Q. And this 3 comes from the fact that this is a index 3 subgroup in D3, so it has 3 cosets. This is not a coincidence. I've also highlighted in blue over here the normal subgroups of D3, and the corresponding subfields over here are actually called normal field extensions of Q. Now we'll study this in more detail later, but let me just give you the informal definition with an example. So this is a normal field extension because I adjoined a root of a degree 2 polynomial and I get the other root for free. It's automatically in there. Recall that the other root is negative zeta minus 1. Whereas over here, I adjoined a root of a degree 3 polynomial, cube root of 2, but I don't get the other 2 roots in that field for free. The other 2 roots are not real, like zeta cube root of 2 is not a real number, and this subfield is contained in R. So these are not normal field extensions because when I join a root of a polynomial, I don't get all of the roots, whereas this one is normal. And it is not a coincidence that the normal field extensions correspond exactly to the normal subgroups. Hopefully, I've piqued your interest about this amazing connection between subfields and subgroups, which is at the heart of Galois theory. So let's step back and summarize what we've learned about fields so far. Roughly speaking, a field is a group under both addition and multiplication, well, that is the latter if we exclude 0, and the distributive law connects these two operations. We are mostly interested in the field of rationals, denoted Q, and certain extension fields, F of Q. Now we can do this whole thing over finite fields like Z2 and ZP, and we can get a lot of the same results, and sometimes they're a little bit different, but this is the best way to begin, and that's all we are going to look at, and it's probably the most relevant because it's directly applicable to things like the quadratic, cubic, and quartic equations and the non-existence of a quintic equation. Some of the extension fields that we've encountered include Q adjoined root 2, Q adjoined I, Q adjoined root 2 and I, Q adjoined root 2 and root 3, and Q adjoined zeta and the cube root of 2. Next, an automorphism of a field is a structure-preserving map, and it automatically has to fix the rationals. This is a lot like an automorphism of a group, which had to fix the identity. So here we don't just fix the identity, I guess there's two identities, the additive and multiplicative, but we fix everything that those generate, which are the rationals. The set of all automorphisms of an extension field F of Q forms a group, and it's called the Galois group of F, and it's denoted as GAL of F. This is how we write it. There's an intriguing but so far mysterious connection between the subfields of F and the subgroups of the Galois group of F. And actually, until now, I haven't actually said that that subgroup lattice that I've showed you, like D3 in the example in the previous slide, was the Galois group. So I guess I'm hinting at that now. So there's this connection between the subfields and the subgroups of the Galois groups, and this is at the heart of Galois theory. This is where it all comes together. Let me finish with a question, just something for you to ponder. How the heck does all of this relate to solving polynomials with radicals, and in particular to proving that there is no closed formula for the roots of a general quintic polynomial. So that's something to think about. That's what we will address and answer in the next 2 lectures. And then after that, we will conclude with 2 lectures, purely for fun, of where we apply these tools of Galois theory to some very old problems in geometry that stumped the ancient Greeks. And these problems can be solved quite easily with our tools from Galois theory. So stay with us.